Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 5. Newton-Cotes Rules. Newton-Cotes rules are a family of numerical integration methods used to approximate the definite integral of a function. The Newton-Cotes rules are based on approximating the integrand by polynomials and integrating the polynomial exactly. There are basically two kinds of rules, open and closed, that make up a family of formulas for the numerical integration of uniformly spaced integration points. The open or closed rules differ in how they handle the interval endpoints. In the open Newton-Cotes rules, the endpoints of the interval are not included in the integration points, which can yield improved accuracy or efficiency, especially for certain types of problems. This distinction is based on the choice of abscisses used in constructing the approximation polynomial for the interval from x0 to xn. Any closed rule can be derived by constructing a Lagrange interpolating polynomial of the nth degree from a set of n+1 uniformly spaced discrete integration points, where for k equals 1 through n and xk is x0 plus kh with h equals xn minus x0 over n. An approximation formula, uppercase f as a function of f0 through fn, is obtained by integrating the interpolating polynomial over x0 to xn. A general family of numerical formulas is called closed Newton-Cotes rules because they include the integrands at both ends, i.e., f0 and fn. Some of the closed Newton-Cotes rules, with the local error terms, are given as follows. The most commonly used closed Newton-Cotes rules were covered previously. Thus, this lecture is largely devoted to the application of open Newton-Cotes rules. Any open Newton-Cotes rules can be derived by constructing a Lagrange interpolating polynomial passing through n-1 uniformly spaced discrete integration points. As in the case of closed formulas, the polynomial is integrated over the interval from x0 to xn. The simplest case in this family, also known as the midpoint rule, requires two rectangular panels of width h. The approximate integral of fx from x0 to x2 is set to the midpoint value p0x equals f1 times the interval width 2h. The midpoint rule has a third-order local truncation error. Another rule can be obtained by dividing the integration interval into three uniform panels. Excluding the endpoints, the interpolating polynomial passing through points A and B is a straight line. So, integrating p1x from x0 to xn gives the following rule, which also has a third-order local truncation error. Similarly, integrating a second-degree interpolating polynomial over the prescribed interval yields a fourth-order rule. Higher-order open Newton-Cotes formulas are also available. Here are a few more. Open Newton-Cotes rules are generally not applied to regular smooth functions. They are useful only when estimating certain improper integrals, where the integrand is discontinuous at the lower, upper, or both endpoints of the integration interval. The advantages of the Newton-Cotes rules are: open Newton-Cotes formulas are simple and easy to program. Formulas of high order of accuracy are available. They are effective in treating the integrands that have singularities at the endpoints. They can be easily adapted to composite rules. A Newton-Cotes rule based on n integration points yields the exact value of the integral for polynomials of degree at most n-1. They are used in multi-step integration procedures in the numerical treatment of ordinary differential equations. The disadvantages of the Newton-Cotes rules are: the integrand must be smooth to ensure the specified order of accuracy. Very high-order accurate integration formulas are rarely used in practice because they also suffer from Runge's phenomenon. Errors can be very large for large integration intervals, which requires the use of a composite rule in most cases. The convergence of any open formula can be very slow for integrands with singular points. For n greater than or equal to 2, the weights become larger and alternate in sign, which can be a source of instability, in particular, due to the propagation of rounding errors. Now, let us use open Newton-Cotes rules to estimate the following integral. We will divide the integration region into n equals 1, 2, 4, 8, 16, etc. subregions and apply the midpoint, 2-point, and 3-point rules to each subregion to estimate the integral. The function f(x) has a discontinuity at x equals 1, but it has a definite integral, which is equal to 2. We identify the abscissas and note that 2h equals 1. Treating the integration interval as a single region, the midpoint rule yields 1.414214. Next, we split the integral into two integrals over the subregions with a width of 0.5. We find the midpoints of each region and corresponding ordinate. And then we apply the midpoint rule to each integral. Performing the numerical calculations, we obtain 1.577,350. Splitting the integral into four integrals over the subregions having a width of 0.25. We find the midpoints of each region and evaluate the integrand at the midpoint. Then, we apply the midpoint rule to each integral. We find 1.698,844. The 2-point rule requires 3 panels, or equispaced 2 points for each region. Treating the integral as a single region, we calculate the function values at 1/3 and 2/3. After doing the calculations, we find that the estimate is 1.478398. Next, we divide the integration into two equally spaced subregions and apply the 2-point rule to each integral as follows. Substituting numerical values, we get 1.6254,326. The 3-point Newton-Cotes rule requires 4 panels and uniformly spaced 3 interior points, labeled as 1, 2, and 3, excluding the endpoints 0 and 4. When we approximate the integral as a single region, we estimate the integral to be 1.631729. After splitting the integral into two integrals of uniformly spaced subregions and applying the 3-point rule to each subregion, we obtain the result 1.739342. We can increase the number of points to derive a high-order accurate open Newton-Cotes rule, but high-order rules suffer from Runge's phenomenon. Thus, we prefer to use a low-order formula together with the composite rule. Here, we have tabulated the results for increasing numbers of subregions, n, where the chosen Newton-Cotes rule is applied to the subregions. Note that, using the midpoint rule, increasing the number of subregions results in improved estimates. When the 2-point rule is applied, the resulting estimates show improvement, but at the cost of doubling the function evaluations. When the 3-point rule is used, the estimates also improve. This improvement is significant for a small number of subregions. This rule is a bit costly as it requires 3 function evaluations per subregion. Notice that in all three cases, the estimates slowly approach the true value of 2 due to the singularity of the integrand. The relative true errors of the estimates obtained in the case of n equals 64 subregions are 3.78%, 3.34%, and 3.26%, respectively. That is all for now. See you next time with another topic. Bye.